Hello, I'm Julian Stander, and I'm going to talk about one of the modules that you can study on the mathematics programs at the University of Plymouth. That's called MATH3613 Data Modelling. So this would be a final year stage 4 module. And I'm going to talk in some detail about what we cover in this module. And as part of that, I'll be mentioning the t-test. So on MATH3613 data modeling, we learn about the parameters of a mathematical model in two ways. And the two ways that we look at are the Frequentist framework and the Bayesian framework. And I'm going to illustrate that now using real data on the price-earnings ratio of 10 companies from country 1 and 12 companies from country 2. So the price-earnings ratio is the price of the share divided by the earnings from the share. So it's a measure of how well the company is doing. So the data are presented in R, which is a free statistical package that we study at Plymouth. And they are shown there in the screen. There are the 10 values from companies in country 1. And there are the 12 values from companies in country 2. And I've also displayed those data using a box plot, which we can see there. And what we learn from this box plot is that the boxes are somewhat different, but they certainly overlap each other. And so what we want to understand better is the differences, if any, between the two countries. Okay, so we have 12 data points from country 1 and 10 data points coming from country 2. And in this display, I've slightly jittered or moved those data points so that they can all be seen, because there are some overlapping values. So what we usually do is we form a mathematical model. And in particular, in this case, we could use Y to represent the price-earnings ratio. And then our mathematical model would be the 10 values of price-earnings ratio coming from country 1 following normal distribution with mean mu1 and variance sigma squared, where those parameters are considered to be unknown and have to be estimated. We have to learn about those parameters from the data. So if I represented this, well, the normal distribution looks something like this. So the bell-shaped distribution, something like this. This is the mean, mu1. And what the model says is that the 10 values, there they are, for example, the 10 values of price-earnings ratio from country 1 follow that distribution. So you get more values near the center of that distribution and fewer values out in the tail. And similarly, for country 2, we've got 12 values, and they're assumed to follow a normal distribution with mean mu2 and variance sigma squared again, so the mu2 would be unknown. And so picture here would be that you have possible values of y, your mu2, and then the distribution with the same spread, and those 12 values would come from that distribution. And what we really want to do is learn about mu1 and mu2 from the data. And you will probably have met a way of doing that, learning about those parameters, which is referred to as the t-test, or more precisely, the unpaired t-test. And the idea here is that we have two hypotheses that we want to check. The null hypothesis is that mu1 equals mu2. So the mean of the mathematical model, the mean of the normal distribution for the first country, country 1, is the same as for country 2. And the alternative is that those means are not the same. So those are the hypotheses that are tested in the standard unpaired t-test. Sometimes those hypotheses are written in a different way as mu1 minus mu2 equals 0. So there's no difference against the alternative that there is a non-zero difference. So how do we do any statistical test? Well, the first thing we have to do is compute a test statistic. And in this case, it turns out that the test statistic is 0.657. So we can actually compute that test statistic in R, or we can do it by hand. So in the code that I'm showing you there, there's a computation of that test statistic, and there it is, 0.657. So that is, in a sense, a measure of the evidence that the data provide against the null hypothesis in favor of the alternative. But in practice, what we tend to do with this is we compare it with a particular distribution. And in this case, when we do a hypothesis test, we look at the distribution of the test statistic, and it turns out that the distribution of the test statistic is a t-distribution on 20 degrees of freedom. And this 20 comes from the fact that we have 12 observations in the first country plus, 10 in the first country plus 12 in the second country minus 2, which is 20. So we end up with 20 degrees of freedom. So what do we actually do when we do a statistical test? Well, we look at the distribution of the test statistic under the null hypothesis, and we fix a level for the tests. So if we usually test at the 5% level of significance, this means that we cut off 2.5% in each tail. We're doing a two-tail test. And the rule is that we reject the null hypothesis if the value of our test statistic is in that tail. And it turns out that you can check using a package or using tables that the value that cuts off 2.5% in each tail is 2.09 and minus 2.09. So if the value of the test statistic is greater than 2.09 or less than minus 2.09, we will reject the null hypothesis. Now, our test statistic there is 0.657, so it's going to be about here. And that means we do not reject H0. And therefore, we conclude that the underlying mean differences in the price-earnings ratio for the two countries are the underlying difference is 0, that there is no underlying difference. So we do not reject H0, and therefore we conclude that mu1 minus mu2 equals 0 or mu1 equals mu2. So that's the standard t-test that we've studied before, we may have studied before. And that t-test is an example of frequentist analysis. Because it's based on the idea of taking many samples of the data. So it's based on a repeated sampling idea, or in other words, it's based on the idea of frequently sampling the data. Hence the term frequentist. Well, there is a popular modern alternative to the frequentist approach, and that's the Bayesian approach. And the Bayesian approach takes a slightly different way of thinking about the mathematical setup, and it's based on expressing what we know about the parameters of the model after seeing the data, expressing that in terms of probability distributions. So the basic idea of the Bayesian approach is that we can express what we know about the parameters of the model after seeing the data as a probability distribution. And this is the key idea of the Bayesian approach. It's all about expressing our beliefs about the parameters of a mathematical model once we've seen some data, expressing those beliefs using probability. So here's an example in this present case. I'm not going to run all of that code or explain it, but I'm going to show you the results of that code. And if we look there, we end up with a probability density function for the unknown parameter mu1, and also a probability density function for the unknown parameter mu2. So, for example, what we end up with, as we've just seen, is a probability density function. So, for mu1 after seeing the data. Sometimes this is referred to as a posterior. So what I've got there in my plot is what I believe about the parameter mu1 of the model after seeing the data. And that's centered around 36. And this probability density function here, this posterior belief about mu1 after seeing the data, is computed for us by a state-of-the-art package called STAN, which we also study on this module. As I said, we can get a similar plot for mu2, and in fact, that's the plot I've been showing there. So the plot for mu2, equivalent one, is slightly lower down, and it's centered at around 30. Well, that's nice, but we can do even better, because in fact what STAN allows us to do is to express our beliefs about combinations of these parameters after seeing the data. And the combination that we were interested before was mu1 minus mu2. So what we can do is we can ask the computer to produce a plot of what we believe about mu1 minus mu2 after seeing the data, and that's shown there. And that's a very powerful feature of the Bayesian approach, that we can work with combinations of parameters. So this is a probability density function of mu1 minus mu2 after seeing the data. And that looks something like this. You can see exactly what it looks like from the computer. We first of all note that that probability density function is consistent with the value 0, which again links up to what we saw with the t-test. But we can also ask ourselves the question, what's the probability, just as an example, that mu1 minus mu2 is greater than 0 after seeing the data? The Stan software will do that for us, and the answer turns out to be 0.74. So what we have in the Bayesian framework and what we study on this module is an easier way of quantifying our beliefs about the unknown parameters of a mathematical model after seeing some data. And that's called the Bayesian framework. And it's really nice because we can quantify our beliefs using probabilities and probability density functions. Thank you very much for your attention.